I mean, if you have uranium in water and you want to pass it to the kerosene, it's normally because you want to separate that uranium from something else. So this is a more complete picture of what we may have. For example, this A can be uranium, as usually B can be the fission products that you want to separate from uranium. So you have opened the rod with a nuclear fuel that contains uranium, that contains fission products. You have all of them mixed in a nitric acid solution in water. So all of this is together, and you want to separate. The fission products will go to a waste stream to store it, and the uranium you wanted to recover it and use it again as fuel. Yes?
This just reminded me, one of the main fission products is iodine, and iodine is far more soluble in organic solvents than in water. How do you prevent iodine accumulating in the kerosene flow?
Well, we will see that later, but basically you can change with the conditions. So you can have, for example, it will accumulate. So basically what you have is a first extraction. So you have something which is more soluble in the organic solvent. So in that case, you need to design your system.
Okay.
So these compounds go to the kerosene phase. Normally, having said that, normally what you do is the extraction is based on keeping the fission products in the aqueous phase and extracting the uranium. But you can always design your system. So have conditions that make uranium to be more likely to stay in the aqueous phase. For example, don't use acid. That increases the affinity of uranium for the aqueous phase.
Or even you run the very first stage without the phosphate in the kerosene, because uranium is soluble
exactly.
because of the phosphate.
That's the reason why phosphate is used in the kerosene phase, is to promote uranium extraction. If you don't want to extract uranium, you want to extract something else, you will use the opposite condition. But yeah, that's a good point. So again, conditions will need to be tailored to the separation we want to achieve. But basically what we want is, well, what do we want here? So imagine A is uranium and we want to extract it. So how would you measure how good your system is? So when you look at all these numbers here, what would be relevant? What do you want to achieve? So if you had to impose some target on your system, what would you be looking at?
Separation achieved.
Sorry, who? XVN? Okay, so yeah, you would want one of these numbers to be very small, the other large. So yeah, you want a big difference. So ideally, say, if we are extracting A would be 0 and B would be XV naught, for example. Is that right? So imagine that we want to extract A here. We want A to move to the kerosene phase. Then we would like to have almost no A here. You know that to have 0 A here it's likely to need infinite stages, but you want this number to be very small. And you want B not to change much, so to be as close to XV naught as possible. So what on the other side? What on these numbers here? What do you want to be high here? YA1, YB1, both, no?
YA1.
Yes, if you extract a lot of A, YA1 will be high. YB1 you want to keep low. So you want to extract A without extracting B, basically. So this has to be low, again, because all the B will be there. And you want to extract all the A here and have little A left at this exit. Okay, does that make sense? So again, you can work out the equations for the loss of both of them. You may remember we've seen this before. So this is the loss of A, so the A that is still in the system that was not extracted at this point. So that's as a fraction of the initial A. So you can have, say, 1% of the A left. Similarly for B. So again, you want the loss of A to be small, and you want the loss of B to be a large number, according to what we discussed earlier. This is how they behave. I'm not going to go into a lot of detail because the problem we're going to see later today relates to having two solid spheres. But you can calculate the number of stages for a given separation. So if you input here the loss you want, you can calculate the number of stages that will give you that. And again, if you want to know where these equations come from, just check again the slide for our previous lecture, which is how the Tensor-Chowder equation was developed. So this is the sort of thing that you will have. Typically, you will have a case in which the extraction factor is large for A and small for B, again, because we want to extract A and not B. And this calculates then, or you can work with these diagrams to calculate XA at the exit and XB at the exit, and therefore to find the loss of both at the exit. Is this a good situation, what is shown there on that diagram? Is this a favorable diagram?
We can't get B out.
Hmm?
You can't get B out.
And is that good or bad?
That's pretty bad. You want to get it out.
Why? Okay, so you have here A and XB naught, right? And you will have here XAN and XBN, and then here you will have at this point YA1 and YB1. So it's actually a good thing. If you don't transfer B to the organic phase, so it will end here, so you have a large loss, the way we have defined this. But in this case, we want a large loss of B and a small loss of A, so we have a good separation, right? And this is what we have, a good value for A. And for B, well, if you manage to reach that pinch point there, you may just be working around that, and as I said, B almost doesn't change, so the loss would be 100%, which is the best scenario. So no B is transferred to the organic phase. Is that right? Does it make sense? Any questions? Let's define a couple of things that these are just definitions, just to call things, give names to some things. But I hope you will agree with me that this makes sense. So first, enrichment of B, and we are going to do this for the heavy phase, or for example for the aqueous phase. And according to this definition then, so look at what we are doing. We are comparing the ratio between B and A at this point, at the exit of the system, so here, XBN over XAN. So this is at the exit of stage N. And we compare that ratio with the original one, xb naught over xa naught. Okay. So, according to what we discussed 5 minutes ago, do you agree that this is an interesting definition? Because what do we want? A large enrichment or a small enrichment of B in the heavy phase? We want this number to be large, right? So, because we wanted to transfer A, so we wanted xan to be small and xbn to be large. So we want this to be a large number. So look at that. This is just the ratio at the exit divided by something which is a constant given your conditions, because normally this is something that you have control of, that is given. The inlet is normally a given. So you are assessing here how good the separation is. So again, it's just a definition, but I like to highlight that it makes sense according to what we discussed. So we can say we want a high enrichment for B in the heavy phase. There is another parameter which is enrichment of A in the light phase, which has another name as well, which is the contamination factor. Right? So as you can see, the definitions are the same. So what we call the decontamination factor is basically something that will assess how much A has been transferred here. So we will have the concentrations in the light phase, that ratio, A to B in the light phase, over, again, as you have there, XA naught over XB naught. And which is, so basically this is a measurement on how good the output is as compared to the input, right? So the denominator in both cases just compares the input conditions, so we can benchmark against the input condition. So this actually describes how well your system works, and it doesn't depend on whether this ratio was 100 to 1 at the beginning. So again, it only depends on the system, not on the inlet conditions, because we are normalizing for inlet conditions. Right. So it's clear. These are basically the two definitions that you will need to know when comparing different or systems with different solutes. So, if that is clear, just tell me for this system. Okay, so we have 6 stages. We have a field which has A and B. We have our equilibrium lines that in this case the value of M is constant. And well, imagine this is our case. What can you tell me about enrichment and the contamination factor? First, would I have a large enrichment of B in the heavy phase?
Not really.
Was that?
Not really.
Not really.
All half of it gets extracted.
Yes. So you have a large fraction extracted. I agree with that. But on the other hand, the value for XAN is very small. So I would say that when you look at this ratio, this will still be a large number, right? So because, well, you still have all this B left, but very little A. So I would say that if you look at this, the enrichment can be good. But what is the problem that you are pointing out there? Where would that appear? Well, you still have a large transfer of B to the organic phase, and that will show us a large value here of YD from stage 1. So basically, the issue here is that the decontamination factor cannot be as good as we want. It can be rather low now. Okay. So this is just an example to give you an idea how these numbers, enrichment and decontamination factor, can be applied to assess a system. So when you have the numbers and how they Right. Following that, let's move on, and I'll show you very briefly some equipment that is used for extraction. So far we have only drawing some diagrams. You can have still our mixer and settler unit, which is something of this sort. So you have a vessel with good contact with interfaces, followed by another one where they are left there to be separated, and you can have a continuous system here. Other equipment, well, this can be just a combined one, rather than in different units, part of the same equipment. So you have the feed, some steering here, so this is where the transfer takes place, where the contact occurs, and then this moves out of the mixing area to the separation, where you have an organic phase and an aqueous phase, and in the middle you will have a band where disengagement of the phases occurs. And of course the organic phase is taken from there, from the top, and the aqueous phase from the bottom, so you don't take from the dispersion band and you're collecting pure phase. This can be done in columns. So the kerosene would go at the bottom and the water at the top. Why is that? Yes, exactly, because you want them to mix, so the kerosene, based on the lower density, will go up, the water stream will go down. You collect the heavy, the water solution at the bottom, the light solution at the top, and this provides a very good contact. So you have bubbles that deflect the solutions, provide good mixing, and enhance the transfer. And the number of stages is typically something that you can calculate here. So, for example, certain distance on the column acts as one stage where an equilibrium is reached, right? So it's not as obvious as in this case, where each of these is one stage, stage 1, stage 2, stage 3. Here in a column you can have, in the same equipment, the same column, you can have 5, 6, 7 stages, 15 stages, whatever, depending on the design of the column, right? Well, there are various different designs, all based on the same principle. There can be some mechanic agitation instead of buffers. The particle size can be made smaller, so by having a fine spray there, improving the contact area, but again it's another design with the same basics. Or you can have plates which are perforated, so you can allow the flow, of course, and these plates will again enhance the contact between the two phases. A similar function has the packing in packed columns. So this is some inert material that is there, a solid that doesn't dissolve, doesn't interact, doesn't absorb any uranium or anything else that you have in there, but provides different paths for the flow and enhances the contact. So this is what we've seen. This finishes all the theory about solvent extraction. So what I'm going to do next is to switch to the application, and I'm going to show the direction process. If you want, we can have a 5-minute break now, given that we are changing topics, so it's a good time. And then we're going to see how solvent extraction then is applied to an actual separation.